Hi, Algebra 2A students, it's Miss Carol here, and I just wanted to welcome you to the course and to let you know that this is how I intend to do projects in this course. So basically, they're kind of like participation points, and if you watch these videos, you should be able to accurately answer all the questions in each of the 6 projects. So I want to keep these videos short. So let's go ahead and we're going to work through the Kingdom Divides Lesson 1 project questions. Here's the background information, and it'll be the same for all of Lesson 1, or I guess for all of Unit 1. Wizard Engineer, who works for Queen Parallella, is now working on some electric circuit problems. He thinks you can help him solve these problems because you know about complex numbers, which can be applied to electrical circuits. So before moving on to the problems, Wizard Engineer wants to give you some basic information about electric circuits and their relationship with complex numbers. Quantities in alternating current circuits, or AC circuits, where the electric charge changes direction periodically are expressed with 2 dimensions, amplitude and phase shift. In order to analyze AC circuits, complex numbers are used to express 2 dimensions, amplitude and phase shift, of such quantities as voltage, current, and resistance. Voltage is the amount of potential energy between 2 points on a circuit, and it is measured in volts. Current is the flow of electrical charge and is measured in amperes, and we shorten that to amps. Resistance is the material's capacity to resist the flow of current on a circuit, and that is measured in ohms. 2 basic types of circuits are series circuits and parallel circuits. A series circuit is a circuit in which components are arranged end to end so that the current only has one path to take. The current is the same through each component. A parallel circuit is a circuit in which components are arranged in a way that the current is split between multiple paths, and the voltage is the same through each component. All right, so the current is the same with the series, and the voltage is the same with the parallel. All right, so let's go ahead and we're going to solve these problems. We are going to use J instead of I, because in electronics they use J to represent imaginary numbers, because I usually means current. So our complex numbers are going to be written as A plus JB instead of A plus IB. Okay, so question 1. A series circuit is a circuit in which components are arranged end to end, and we kind of already went through this. The total resistance of the circuit is the sum of the resistance values of each individual component. If the resistance of one component of a series circuit is 3 plus J5 ohms, and the resistance of the second component of the circuit is 5 minus J8 ohms, and the resistance of the third component of the circuit is 6 plus J4 ohms, what is the total resistance of the circuit? Okay, so this is no different than we've done before, where we can just add the real parts of the number and add the complex parts of the number. Okay, so if we add 3, 5, and 6, we're going to get 14. And if we add 5 and 4, we get 9. And then if we subtract 8, we'll end up with a positive 1J. So our real component is 14, and our complex component is just simply 1J, or 1 imaginary unit. And so our answer here, I guess I can probably click on here. There we go. Our answer would be that 14 plus J ohms. So hopefully that made sense. Okay, question 2. A parallel circuit is a circuit in which the components are arranged in a way that the current is split between multiple paths. The voltage is the same through each component. The total current of the circuit is the sum of the current values through each individual component. So I'm told that the total current of a parallel circuit is 9 plus J2 amps, and the current of one component of the circuit is 3 minus J5 amps. So what is the current of the other component? So basically, in this case, we're going to just rewrite this as the total being 9 plus J2 equals 3 minus J5 plus I2, okay? And so I should just be able to move these over to the other side to get the other component. Okay, so if I subtract 3 from both sides, that'll leave a 0 here, and I'll be left with 6. And now I need to do my imaginary unit, so I'm going to add J5. Okay, and that will give me my J7. So my second component of this circuit is 6 plus J7 amps. Okay. Question 3. The scientist George Simon Ohm, or George Simon Ohm, developed a formula known as Ohm's law that relates the voltage, current, and resistance in a circuit. In Ohm's law, V represents the voltage measured in volts, I represents the current measured in amps, and R represents the resistance measured in ohms. V equals IR. And if you haven't taken a physics class yet, you will end up seeing this a lot. What is the voltage in a circuit if the current 5 plus J3 amps, if the current is 5 plus J3 amps and the resistance is 3 minus J2 ohms? Okay, so for this one, we are given the current I and the resistance R, so we need to solve for V. So we need to multiply these just like we would do multiplication for two binomials. We can use FOIL. All right, so we've got 5 plus J3 times 3 minus J2. And I'm going to do first, outer, inner, last. Okay, so first terms give me 5 times 3 is 15. Outer terms give me 5 times a negative J2 gives me a negative 10, a negative J10. I guess we put that in front. There we go. Inner gives me a positive 9, or J9. And then my last terms give me positive 3 times negative 2 is a negative 6, and so this is J squared. Negative J squared 6. Okay? But just like we looked at previously, this J squared is the same as a negative 1, right? So this is basically the square root of negative 1. And if I square the square root of negative 1, I get negative 1. So this becomes a negative times a negative 1 times 6, which becomes positive 6. Okay? And then now I can combine like terms. So my real numbers become 6 and 15 gives me 21. Oops. Let me erase that. Sorry about that. 21. And then I've got a negative J10 and a positive J9 gives me a negative J volts. Okay, so 21 minus J. And that's how we did it, just using the FOIL method. Okay, so let's move on to question 4. And here we go. Okay, so this one we are given voltage of 35 plus J12 volts and a resistance of 2 plus J4 ohms. And so since we have voltage and resistance, we need to rearrange to solve for current. So this should be pretty simple for most of you. I equals V over R. Okay, and so we are going to say that I equals 35 plus J12 over 2 plus J4. Now we could have gone and just tried all of these and solved by process of elimination, but we do actually have a pretty clear mathematical way to do this. We can't divide directly here. What we need to do is simplify this because basically we're looking at a rational expression, and so we can treat it like a rational expression. We can multiply this by 2 minus J4, and that's going to create a difference of squares scenario, which is going to end up working out really well for us. But if I multiply the bottom of this expression by 2 minus J4, I need to do the top too. So same thing with the top. All right, so I'm going to go ahead and use the FOIL method on top, and when I do that, I am going to get 70. My outer terms are negative 35. Oops, negative 35 times 4 is negative 140, actually. Let me erase that. So my outer terms give me negative 140 J plus 24J is my inner terms. And then my last two terms are minus, and I know J squared is the same as negative 1, minus negative 1 times 48. 4 times 12 is 48, okay? And then in my denominator, as this is a difference of squares, I am going to end up with 4 minus J8 plus J8, and then minus a negative 1 is the J squared times 16. So pretty cool. These actually end up going away, and we can start combining like terms. So 70, this ends up being plus 48, gives me 118. Okay, and then minus 140, negative 140 plus 24 is a negative 116. Okay. And then that is all going to be over 4 plus 16, which is 20. Okay, and now I can start reducing. Okay, so when I reduce, I can see that 118 and 20 are both divisible by 2. So when I do that, I get 59 over 10. And 116 and 20 are both divisible by 4. So when I do that, I get 29J over 5. So if you wanted to check your work on this, you could plug it back into the original V equals IR and solve. But this is, I'm going to tell you that that is the right answer. And then when we get to question 5 here, you can write out what I did for 2 and 4 if you'd like, or you're welcome to just say that you watched the recording, because I will then know that you worked through it. And really, I'm doing this for participation, and I do hope that you learned something from these recordings. So anyway, I hope that is helpful, and I thank you so much for 15 minutes of your time, and I'll see you back here for lesson 2.